Hi, this is Alina. In this project, I'm going to show how I use the A-star algorithm on neural network to help AI vehicle find the best path in Unreal 5. In this demo, I'm using 100 auto-driving vehicle to test the traffic behavior. Each car uses A-star to find the best path from its current position to its destination. They stop at red lights, make regular turn or U-turn, change lanes, overtake other vehicles, reverse, and also slow down on curved and uphill roads. You can switch to any car you want and reset its destination at any time. Standard A-star work with predefined nodes, but that's a lot of work if I had to manually define every node and every intersection for each map. So instead of that, I built a pipeline that automatically covers road splines into graph for using A-star. The reason that R²S² cannot use S or A-star edge directly is it's more convenient for artists to separate one row as many different splines. For instance, they probably want to put a tunnel in the middle or change your material. So at the beginning, we treat each spline as one edge candidate. Then for every spline, we collect its start and end points and add len O into nodes candidates. After that, we merge nodes that are close to each other into a single node. This way, separate splines become connect as one path in A-star. But intersection can also happen in the middle of the row, so I use two algorithms to find this junction. In the brute force algorithm, for every pair of rows, we compare each point on row A against every point on row B. That means we have a double for loop. S is the number of sample points per row. That means both of row A and row B have S points. So for one pair, that's S times S comparison. And R is the number of rows, so in total, we are doing R² times S² comparison. For example, if we have a 100 row and 200 sample points each, that's 100 square times 200 square. So that the total will be like 400 million operations. The problem is we are computing the distance between points even when they are really far away. But the grid hash algorithm is different. Instead of comparing everything, we divide the world into a grid. Each point only looks at the point in nearby cell. So instead of comparing against all the points, each point only checks k neighbors, and k is a constant. It doesn't grow even if the map gets bigger. With the same total points, and we choose k as 50, that's only 1 million operation, which is 400 times fewer than brute force. So how does grid hash actually work? Since we already merged different splines as our edge candidates, we can sample points along it at the regular intervals, so instead of working with the whole curve, we just work with the least sample points. When two rows cross, their sample points will be very close to each other, and that's how we detect a junction. Now, the right side of slide shows the key idea. We divide the world into a grid. Each point only compares with points in their neighbor cells. So points A and point B are in their nearby cells. We will just compare their distance to see if they are a junction. But point C is far away in a different cells, so we just skip it. And that's the whole point. We don't need to check a C at all, and we save a lot of time by just skipping points that are obviously too far away. So here is the time complexity, and we already talked about the example earlier. And this slide shows the code difference. Brute force has a for each loop. It compares every point against every other point, no skipping at all. Grid hash has the same structure, but the inner loops are much smaller, only 27 nearby cells, so around like 50 points each. That's where all the speed up comes from. The flow is basically the same, Both algorithms find junction the same way. The only difference is that a grid hash insert points into a grid first. So when we get to the comparison step, we only look at nearby cells instead of everything. And this graphic shows that for small maps, it doesn't matter much. But for large maps, brute force just doesn't work anymore. After we find candidate junction pairs, we apply a few filters to remove invalid ones. For example, we skip pair from the same row, and we skip a duplicate pair like A to B and B to A, and we do the final distance check, and skip the endpoint to endpoints connection, since those endpoints are just like a normal row joins. And if a multiple pair detect the same junction, we merge them into one. This filter makes sure the final result is clean and accurate. So let's check about the demo. This yellow car's destination is on the back, so he needs to make a U-turn first. There is a big difference with regular A star since you can just choose the closed row. I can switch his destination to any location I want, but after changing the destination, you can just turn back immediately. So my game logic is you can only make a U-turn at the intersection or the end of the dead row, and the side of the location matter. For instance, since this car is going to make the left turn, he will just automatically switch to the inner lane like 500 meters earlier. And let's check about the switch lane function. At the beginning, I only set a rule and you will automatically switch to inner lane when, first, you are going to make a left turn or U-turn. Second is the overtake function. When somebody is stuck in front of you, you can see the status on the right information panel. Or you will also switch to outer if you are going to make a right turn. But it's getting so much more complicated since after I put 100 car in and my map is not that big. So I add the condition that it's alright if you don't switch lanes during the traffic jam if somebody block you or they are coming behind you. You will just start the turn from the outer lane but lerp into the inner lane. I was more focused on the AI part since I only have a few weeks to do the project, and the gameplay logic can easily be replaced later. So I was thinking about building a tool like a Google Map, and every vehicle can have a different way to approach a destination. For instance, each car have a different speed, accelerate and decelerate rates. I feel it's more natural since some people may use hard brake pretty often. For the turns, I have tried Hermit's curve and Bezier curve, but the tricky part is every row has a different width. I have a 2-lane row, 4 lanes, and one with a bridge in the middle, so I use a semicircle for the turn instead. It's more mathematic, but more reliable since I need to automatically calculate the radius based on different row widths. Both of the slope and curve matter. You can see the speed draw from the information panel when it passes by slope and curve. I feel that's more realistic. Well, the highway I built is not that realistic, but I just want to show that my A-star algorithm would merge the highway and the regular road since it shouldn't be a junction. Also, I place landmarks on the map. These landmarks are not A-star nodes. Because A-star has to manage all nodes, if you turn every landmark into a node, it would be too heavy on performance. In my previous setup, A-star nodes basically only come in two cases. First, edge where two splines are connected. But in gameplay, I actually disable U-turn in this case. Even though it's an A-star node, it's still basically the same row, just split into different splines. The other case is junction found by grid hash. So the A-star system is node-to-node navigation, but it feels weird if a car can force to stop at an intersection. So now my A-star setup allows car to start at any point on the map. First, it navigates to the nearest node. Then it projects the destination onto the closed spline, and use a dot product to figure out which side of the destination is on. Finally, it goes from the nearest node to the project points. If the car's direction doesn't match the destination direction, it still has to do a U-turn at the intersection before it can reach the target.